All right, let's start. Today we will learn about the message authentication code and then a little bit of the asymmetric encryption. And before getting into there, let's do a little bit of recap about like the block cipher modes. So we learned about the three different modes: ECB, CBC, and CTR. And for ECB, so this is the simplest mode ever. So what it does is like we will treat the plain text as a plain text and then just run the block cipher out of it. Yeah. Then we will get the result as a ciphertext. That's it. And then we can chain these kind of the block cipher as long as like the message goes like the up. For example, if it is 32 bytes, then like we can run the block cipher twice if the block size is 16 bytes. Yeah. But the drawback of that approach, it's not a drawback, but one of the good thing is that like if we have a specific bit header in the ciphertext, then that will be decrypted in a totally random value. Yeah. So what that means is that like you cannot earn many things even if you alter the ciphertext. Yeah. But the problem of the ECB is that even if you don't know the key, you can launch the substitution attack. So for example, if you want to make this value as a 1, then what you can do is to just copy this value to here. So by overwriting the same ciphertext to the first block, then we can get the first block decrypted as a different value. Yeah. So because of this kind of the characteristics, so the same number will be encrypted to the same number again and again. So it will leak the plain text patterns in the ciphertext. So that's why we can see this kind of the words even in the ECB encrypted graphic file. So another takeaway is that like the ECB, we can encrypt in parallel. We can decrypt in parallel. That means like the encryption and decryption is not depending on the prior step or prior round. And the next mode is CBC. So the intuition of the CBC is that like the problem of the ECB was if the plain text is fixed, then we will have the fixed ciphertext. That was the problem. So if we know that which part of the plain text was which part of the ciphertext correspond to which plain text, and then we can move that block around to like use that value as a valid one. And then to counter that, one easy way to counter that is like including random for every encryption. So when we encrypt the plain text P3, what we are doing is like we are including ciphertext C2, and then that value will be XOR'd to the plain text. And then the plain text, it does not coming from random, but if the block cipher is a pseudo-random permutation, so it is a secure, if it is a secure one, then we can regard this value, ciphertext of the previous round, as like a random number. So that's why inserting this, embedding this as an XOR to the plain text, we are not losing any kind of information, but we can make the plain text look like random. So the resulting input to the ciphertext block cipher will be totally looking like random. So by doing so, we cannot match like some of the plain text by just taking a look at the ciphertext. And then to do that, we need to have a previous block's encrypted result. So for the first block, there's no such block at all. Then to make the first block random, so we need an IV, so-called initialization vector, IV, to randomize, to embed the random, that kind of random to the first block too. Yeah. So the intuition is that like the mixing the random for every plain text, and then we can do that by introducing IV, because the resulting ciphertext will be naturally looking like a random, so we can embed that as a random for the next level. But the problem of this approach is that, so if we can make a specific bit error, for example, changing bit from the ciphertext 1 from 0, then that will be directly showing in the plain text of the next block, because it only be linked with the XOR operation. So if you make any kind of XOR operation here, that will be resulting in like the applying XOR operation at this side. So not just for a single bit, you can change multiple bits like this. So that was the weakness of the CBC encryption. But the good thing about the CBC is that like if we encrypt the image, then it will be totally looking random, so we cannot see the kind of the some character pattern in the encrypted image. And then the last one is the CTR mode. So the counter mode is totally different. So in the CBC, we use block cipher encryption and decryption, but in CTR mode, we only use block cipher encryption. So for encryption, what we do is we just set a nonce, so a random number that can be publicly announced. And then from that random number, we will add a little counter at the end. And then starting with that number, by incrementing 1, we will encrypt the next block. So this number 1, 2, 3, 4, that's how we increment the counter. So per each encryption, what we need to do is like we need to negotiate about like what will be our nonce number. And after that, we can just increase 1 by 1 to encrypt the following blocks. And then how the encryption goes is like we just encrypted that number with the key. Then it will result in some of the random looking numbers. And then we will use this as a random number generator. And then we will apply XOR to the plain text. That's the encryption. So the decryption logic is the same. So we encrypt the nonce and counter, and then we apply XOR to the ciphertext. Then we can get the plain text. But the problem of this approach is that because the plain text and then ciphertext, they are just XOR'd with the result value of this block cipher. So any specific error in the ciphertext will be resulting in the same specific error in the plain text. So that you can apply any kind of XOR value here, then that will be the same as like applying XOR to the plain text value. So we examined like what kind of the modes of the block ciphers are available. And then we have seen that the problem of each approach. So for ECB, we can launch the block substitution attack. And then for CBC, we can edit the ciphertext 1 block ahead, and then manipulating apply some of the bit operations, and that will be directly shown on the plain text of the next block. And then for CTR mode, because only the XOR is the linking thing between the resulting outcome to the block cipher to the ciphertext and plain text. If we apply the XOR to ciphertext, then it will be directly shown on the XOR as in the plain text. And then the reason why we do have like this kind of weaknesses is that the block cipher only give us data confidentiality. So they don't protect about the data integrity. That's why, so we can match and then launch some of the attacks like that. So block cipher by definition, by making a function as a pseudo-random permutation, so the attackers cannot guess what is the direct plain text of that one. But having only that property cannot make the full protection. So that's why the practice attack in the challenges can happen. So the important thing is like that we need to provide both data confidentiality and data integrity to get a full protection. And then we will learn about how to do that with the message authentication code today. And then let's check how we attack the 3 different block mode, cipher mode. So our threat model is that we have a verifier, but the verifier has a secret key. But the important thing here is that we don't have the key. So we are given with the verifier and then a correctly encrypted file, the encrypted user. But we don't know the key, but at least we can know which part of the ciphertext corresponds to which plain text, because our verifier decrypted and showed the result for you. So because we don't have the key, that means like we cannot generate an arbitrary file for the valid encrypted file. But what we can do is we can edit the ciphertext for the correctly generated encrypted user file. And then what we have done is like we change it plain text in some way at our own will. So we can bypass some of the security checks if there's a checks over like the password, is admin, or that kind of UID values. Yeah. So the dangerous operation is that like because we allow the editing of the encrypted.user, that file is available for the attackers. So they can edit that and then they can submit the maliciously edited file. So we accept the real value. Then can we block this kind of the attempt? So we cannot block the attempt itself, but in that sense, is there any cryptographic tool that we can verify that at the time of the using the ciphertext? So we have encrypted that user, and then verifier generated and stored it. But is there any way we can detect that data has been modified by the attacker, not by myself? And then if we can detect that, then we can reject the ciphertext if that is modified by the attackers to prevent any kind of attack. And then there is a tool for doing this, and it's so-called cryptographic hash. And for next, I will describe like what is a cryptographic hash function. So let's imagine an ideal world. So in reality, no such function exists, but suppose there is a function f, that it will always return the fixed size message. So the message will be like 32 bytes or something. Yeah, it could be 16 bytes, 32 bytes, but depending on the security factor. But let's make it as a generating 32 bytes as an example. And then for that function f, one of the property that function should have is that, so suppose you have a result of the message, then it will be very hard to find what generates that message. So in that sense, like for fx equal y. So even if you know y, you cannot guess what is x. So that's one of the property of this function. And then another property of this function is that, so suppose you know fx equal y, and then having a very slight value change in x will result in a drastic value change in y. That means even if you know x-y combo, you cannot correlate any other x prime or y prime, whether they are matching or not, without running the function. So if we have like the function with these three properties, generating the fixed length message, and then getting an inverse function. So the inverse is very hard. And then also we cannot correlate values of them from the one result. So if we can meet all three things, then we can actually protect the data and then detect if the data has been modified or not by storing the message authentication code as, so we will create the message authentication code as like we will have a secret key and then add the encrypted data and then run that with the function. And then I will graphically show you what this means. So what I will do is I will prepare a secret key and then attach the encrypted data. And then I will generate a 32-byte code by running that function. And then I will use that as a message authentication code. So how I will generate the thing is like suppose there's an IV block 0, block 1. Suppose this is a CBC attack case, and we have encrypted data like this. Then what I will do is like I will create the message authentication code by running the function with the prefix as our secret key. And then I will put this message authentication code at the end of the data. And then when the time comes to like read the data, then we have this kind of data. Then we know that the message authentication code will be always 32 bytes. So cut off the last 32 bytes, and then we will run the message authentication code function again. And then we will compare if the result of this one is same as this one. Otherwise, we will reject the data because the data is modified. Then let me show why and how this can detect the data modification. So suppose attacker edited the data. So the red part here, so I marked it as a red, as like you can regard that the attacker modified that part. Yeah. So in that case, when I load this data, I don't know whether this data is modified or not, but what I will do is I will run that function with the secret key and then attaching the data part. And then because the input is different, so the one of the condition that kind of the ideal function should have is that the slight value change in x for fx and y will result in drastic change in y. So what that means is that like even if a 1-bit change or like any kind of the data change in here, that will be resulting in a totally different value in MAC. So the result of this function will be different with the existing MAC. So we can reject the data. And then you might be curious about what if attackers can generate the correct MAC. So suppose they edited this file and then they want to generate this kind of MAC. So if they can know the secret key, then they can prepare a secret key and then attach all this kind of data, then they can generate the valid MAC for that. But the problem is that they cannot know the secret key. Even if we release the MAC data here. So what we release is this information. But one of the other property is that you cannot easily get the inverse of the function. So what that means is that even if you know this, you don't know what kind of data generated this message. So even if I release the MAC or many of the results of the MAC to you, then you will never find the secret key. So in that sense, you will never be able to generate the matching message for the edited one. So the implication is that, so what we will do is when we storing the message with the data integrity, so these blocks are encrypted with the block cipher, so the data confidentiality is preserved. So for data integrity, what we can do is we take the entire message and then attach secret key and then run a cryptographic hash function. Then attackers cannot generate the same MAC without knowing the key. And also any kind of the data alteration will be detected by just comparing the MAC. So that's the implication. So any questions? Then let me get into the specific examples of the cryptographic hash. So cryptographic hash is the hash function that is designed cryptographically to have the certain characteristics. And then those characteristics are, the function need to be one-way function. So there's no inverse function. And then it's very hard to find x for given y for hash of x is y. So for given hash message, it's really hard to find what was the original message was. Yeah. And then second characteristic is that even if you know x and y, the mapping, it's very hard to find the x prime. The other x corresponds to the same hash message. Yeah. So the cryptographers they carefully design the cryptographic hash function to have these kind of the characteristics. So SHA-256 is the one of that function. So this is the example of the running of the SHA-256. And then SHA means the secure hash algorithm, SHA. And then 256 means that the length of the output message. So it's a 256 bits. So that's why it's 32 byte. And then if we run the SHA-256, so we can run this kind of hash function to any length messages. There's a no limit. But if we run it with the hello world, then it will convert that message into this 256-bit integer. So SHA-256, SHA is from the secure hash algorithm. And then like this algorithm is in the SHA-2 standard. There was a SHA-0 and SHA-1, but then right now we are not using them because like they are believed to be insecure because our computing power is strong enough to break those things. But right now the SHA-256 that is also still believed to be secure. So like if you want to use a cryptographic hash algorithm, please refer to SHA standard and then try to use the SHA-256 or like the better algorithm. There's another standard called the SHA-3. So that was finished and then like the algorithm was announced, but we practically do not need the SHA-3 yet. So that's why we are mostly using SHA-256. And then that's why I'm giving the example of the SHA-256. So input can be any length data, but what it will do is like it will generate a digest of the data as a 32-byte message. So the output will be always 32 bytes. So you can naturally think that like that there's a no inverse function for this one because the domain is like the entire length of the message, but the range is like the 32-byte message. So the range is definitely smaller than domain. So that's why there's a the inverse function. But having no inverse function does not guarantee that we cannot find like the corresponding x, even if we know the y. So there should be some of the sophisticated constructions should be there to make those kind of property. But we will learn about not about the details of the SHA-256, but more about how we can securely use that. So it's a one-way function, and then if we type a hello world, then we can get this kind of the digest. But from the digest, it's really hard to find that which message have generated this one. So the one will challenge this by like you know that the hello world generate this message. Then whenever you see this message, you can map back with the hello world. Yes, that's true. So that we can actually attack the hash algorithm with predefined table. So we can generate a lot of the hash messages of the plain text, and then later we can match that. But that only works if we use hash without the key. So if we use hash with the key, and then if the key is a secret, then like the attackers can never like generate the same message out of it. And then this is the example of the multiple runs of the SHA-256. And then this is actually the file name, but in each file 0, I put message 0 on it. File 1, it contains message as 1. And then likewise, file A contains a message as a 1 character A. And then E contains a 1 character E. But you will see that the result of the SHA-256 sum is like a totally different. So the second characteristics, so if there's a little change in X, then the result will be changing drastically. So that is so-called avalanche effect. So like that is the required property of the hash algorithm to not making any kind of correlation happening between the hash values. So for example, so suppose you know the hash value of 5. So that is like this kind of the big number. And then the cryptographers designed this algorithm for attackers. It's very hard to correlate what is the result of the 4, what is the result of the A or 6 from like knowing this message. That's why like it changes drastically, even if like there's a very small change in the input. And then one of its characteristics is that like even if you know one of the hash value, then it's very hard to find which message will generate this one. So suppose like finding a message that generates the specific hash value. So we believe that like this task will take like the 256 trials. So by just running SHA-256 for all of the message, then you will eventually find the matching one. Yeah, so the cryptographers designed that to be the only solution to find the generating message for the hash value. Yeah. And then because this is right now this is proven to be secure, and then we are actually using this in the Bitcoin mining. So have you heard about the proof of work kind of algorithm? And then what they are doing is they have a transaction block, and then to mine the Bitcoin, what you need to do is you will need to hash this transaction blocks, and then with the sum of the random number, and then that should result in having this many of zeros at the hash value. So to have 1 0 in hexadecimal represents 4 bits, and then maybe it has the 20 or 30 zeros, then that means 30 0 means the 120 bits of your hash value need to be 0. And then to match that, we believe that the computer should compute SHA-256 for 2 to the 120 times. So for the hash algorithms, so what's important is that if we set a something property, so try to match entire hash value, or try to match the 30 digits of the digits in front of the hash value to be 0. So if we set that kind of property, then the only way to match that is just to run and get it. So that's why that's the characteristics of the hash function. And then another property is that suppose you know that the hello world is mapped to this hash value, then it is also hard to find that any kind of the different message that generates the same hash value. So it can be possible because the domain is much bigger than the range, because range is only the 32 byte messages. Yeah, so that's always happening. But the important thing is that there should be no easy algorithm to calculate that. Yeah. And then the last characteristics is that even if there's a small change in the plain text, then the resulting outcome will change a lot. So from the output, you cannot correlate how the original message was. So the implications of the SHA-256 is that the SHA-256 is a cryptographically designed hash function, and then that's included to the SHA-2 standard. And then this is the one-way function. So unlike block cipher is a two-way function. So we can always get the inverse. So inverse is decryption, so that's why. But in the cryptographic hash, we are not encrypting or decrypting. We are just digesting the arbitrary length message, but with the property that, so even if you know the message, it will be hard to find what was the original message. And then even if you know that XY pair, then it's hard to find another message that generates the same hash value. Yeah. And then you cannot also correlate another X from knowing the X and Y pair. Yeah. So what that means is that, so we know that the cryptographic hash function is for the SHA-256, it's hard to find an inverse function. So it's designed to be like that. Then suppose we are generating a hash, something like we put a secret here, and then whenever there's a message, we will attach secret as a prefix and then run the hash function. Then even if attackers know this value, because getting the inverse is difficult, they will never know the secret. Yeah. So that guarantees that. So attackers, they are hard to hard to generate the secret message, because if they don't know the key, yeah, and then property of the hash function will preserve that. Even if they know H, they cannot reveal the secret. So even if they know what the message is, yeah, they cannot reveal the secret, because it's hard to find the inverse function. Then how can we use that? So one of the students asked about like in the message chat about the quantum computer time, but unfortunately, SHA-256 is a post-quantum crypto. So even if quantum computing comes in, SHA-256 is not broken. Yeah. So block cipher and SHA-256, yeah, they are not the target of the broken by quantum computers. So I know that like whenever there's a discussion between like the crypto and quantum computing, there are interesting discussion that like when the quantum computing comes in, then our cryptography was screwed up, but that's not true. So at least for the cryptographic hash and the block cipher, these are secure against the quantum computing. But the asymmetric crypto that I will introduce at the end of this lecture, that is susceptible to be broken by the quantum computing, but we will learn about that later. Then now we have that the cryptographic hash function SHA-256. Then how can we create the hash-based message authentication code? So creating the message authentication code is like we can do that as follows. So for example, we have a hash function as a secure hash function, the SHA-256 as an H. And then to create an HMAC, how we can do is, so suppose there is a secret key, then we can run the hash function with the secret key first. Then that will give us a 32-byte data. And then we will use that as a secret key. So the reason why we run the cryptographic hash function with the key first is to normalize the key size. Because no matter how long your key is, so it could be 4 bytes, it could be 100 bytes, 1000 bytes, 1 megabyte or something. Then after running this hash function, SHA-256, the result will be 32 byte. So we will use hash of the secret key as a real key, and then we will attach that message. So you can regard this 2 bar as a concatenation. So we will attach that message in front of every message that we will generate the MAC. Yeah. Then how it will be is something like, suppose we have some encrypted data blocks. So IVs and then blocks are here. Then suppose you have a secret hash key as a ASDF, just a simple key. Then how we can generate HMAC is we run the SHA-256 for ASDF first. And then put that 32 byte first, and then we attach IV, block 0, block 1. Yeah. Then run, so attach encrypted data, and then run SHA-256 again, and then that will be our HMAC. And then we will store this at here. And then how we can use and check with the HMAC is that, so suppose there is an encrypted data, and then we use HMAC. So HMAC, the hash of the key, attach it with this data, and then create HMAC with that. So we put this kind of the data pair in somewhere. And then later attacker came in. Suppose they edited the data to something else. Yeah. And then, so previous value was 0000, but now the value was changed to like a 1001. Yeah. And then later, I want to check the MAC is valid or not. Then what I will see is like I will calculate the key and the message and then hash it again. But because the input is different, it was 0000, but now is 1001. Then we will have like a different MAC value calculation. So we can reject at this moment. So suppose like when we decrypt the data for the CVC, now we can check whether the calculated MAC is matching to the stored MAC or not. So now we can assume that the HMAC is always attached to the ciphertext for the storing. And then suppose the attacker changes the encrypted data, then we load it, then rerun the HMAC for like from IB to block 1. But because the data has been changed, it will have a different SHA-256 sum. So we can detect that this is not matched with this HMAC, so we can reject the data. Then you might be curious about like the attackers can modify this part and also for the HMAC part. That's possible, but attackers don't know the key. So to generate the valid HMAC, you need to have edited data, but you also need to have the key. But without having the key, you cannot generate the valid HMAC. And then the reason why is because even if you know this message, you cannot get the inverse of it. So you cannot get the what was in there. One question?
Why would you hash the key in the inner parentheses? What's the purpose of hashing?
So like we don't have to hash the key in like for using the thing to the HMAC purpose. And then the reason why we hash the key is like to normalize the key prefix sizes for the 32 bytes. And then that's good for making a proof. So like the cryptographers designed the HMAC to use like the hash of the key. The reason is like if the key size is variable, then for them it's hard to provide a proof. Yeah, but by doing this kind of the structure, they do have a proof that if SHA-256 is secure, then this kind of the construction of the HMAC is perfectly secure. Yeah, so that they can provide a proof, and then that's why we need to hash the key. So even if they know the entire of this value, they cannot get this part out, and also they cannot get the key out of it. So like there's no way that the attackers can obtain the key if it's not leaked. Yeah. So the summary for the message authentication code is that the block cipher modes, they are good for protecting data confidentiality, but they don't have protection against the data integrity. So they let the attackers can freely play with the ciphertext. And then we have seen that by playing with the ciphertext, we can fool the verifier, even if we don't know the key. So that's a serious problem. And then that's because data integrity was not protected. And to protect the data integrity, we can use the cryptographic hash function. And then we learned about the SHA-256 as an example of the cryptographic hash function. And then the most important characteristics of the cryptographic hash function is that it should be very hard to find the inverse of it. And also, if there's a slight change on the X, then there could be the drastic change in the result Y. And then that is called the avalanche effect. And then that is there for like making correlation difficult, even if you know the sum of the results of the hash value. And then HMAC, hash-based message authentication code. It's something like if we have a secret key, we hash the key again, and then attaching that with the message, and then hash it again. So that could be used for the message authentication code for checking data integrity of the encrypted data. And then this kind of scheme is so-called, so encrypt then MAC. So the example that I showed was like there was an encrypted data, and then we are attaching MAC by hashing the entire encrypted data. Yeah. And then this is the only proven and secure composition of using MAC and encrypted data. So what I mean is that there is a different way of using that. So suppose you have a plain text next to here, and then attach MAC to the plain text, and then run the block cipher entirely. So this scheme is so-called MAC then encrypt. So you can prepare plain text, and then you can attach MAC to the plain text, and then you can run the entire blocks to the block cipher. So this kind of composition is also possible, but when we use this kind of the mechanism, then attackers can alter some of the ciphertext, and then there is a way that the attackers can match both plain text and MAC, even if they are modified. So it's not always successful, but it is proven that there is a way to do that. So we don't use this kind of computation because it is proven to be insecure. So important thing is that like if you want to protect the encrypted data, then please encrypt first, then attach MAC later. Yeah, that's the secure way of doing that. Yeah. So MAC then encrypt, this kind of thing. So you can regard that the attaching MAC means that this MAC can only protect this part, not about the ciphertext. Yeah. So that's why we should not use a MAC then encrypt. So this method, encrypt then MAC, then MAC will directly protect this encrypted data. Yeah. Any questions about the MAC and SHA-256? And then at the end of the class, I will demonstrate like how the SHA-256 runs, and then like I will describe the challenges. And then before that, I will move over the public key crypto a little bit, and then we will get back to the SHA-256 examples. So there is a scheme called a public key crypto, and then also called as asymmetric key cryptography. Yeah. Then what's asymmetric key cryptography? So there is a scheme that we use different key to encryption and decryption. Yeah. So think about block cipher. We use the one key, and then that key need to be shared among two parties, and then we will use that key to encrypt the data, and then use the same key to decrypt the data. Yeah. So our notion of the cryptography up to now was like using the one key. But there is a need for like having a different key for the encryption and decryption. And then we will learn more about that in the key exchange part in this lecture, but I will describe that later. But let's take an example of like the public key cryptography first. So one of the prominent and popular public key cryptography algorithm is the RSA. And then RSA, the letter comes from the inventor of the three people, Rivest, Shamir, Edelman. Yeah, so that's why we call this algorithm as a RSA. And then interesting characteristics of this algorithm is that like it has a different key for encryption and decryption. So this is a public key cryptographic system. And then this cryptography is based on the difficulty of the prime factorization. So right now the prime factorization is it takes like the O log n cubic time or something. Yeah, so it's quite slow operation. Yeah, and then like and then this can also be used for digital signature. And then I will describe like the characteristics and then what's this digital signature in this lecture. So don't worry about that for now. Then how RSA works. So I will not go deeper about like the proof or like the why like we need to do in this fashion or something. So I will just describe like how RSA works. So to work with the RSA, we need to choose a two large prime number. Suppose that as a P and Q. So these two numbers are prime. Then we will determine number n, which is a multiplication of the P and Q. And then we will determine another number phi as a P minus 1 multiplied by Q minus 1. So the actual meaning of the so P minus 1 and then Q minus 1. Yeah. And then we will choose a public key, but the public key usually we use another prime, but we use a small prime for a public key. And then we usually use a public key as a 65537. So if you search on the internet, so I bet that like more than 99% of the key you can find on the internet for the RSA key, they will use the public exponent as a 65537. And then there are many reasons, but the reason is that like we need to run an exponent operation. And then if the exponent is big enough, then requires like the longer time to compute. So that's why we are using the small number exponent. But the number 3 and 17 are proven to be insecure. That's why we are using the smallest but the secure prime, so-called this number. Yeah. And then what we will do is, so we choose 2 prime number, and then we can calculate the fee from n and fee from like these 2 numbers, and we also choose a public key, so 65537. And then what we will do is, so based on this information, we will find the private key D, and then its property must be D multiplied by E should have a remainder 1 if it is divided by this number phi. Okay. So there are some of the number theory details about like the why we need to do that, but the important thing here is that the D multiplied by E will become 1. Yeah. And then by knowing this number, it's easy to find that. That's the important point. Then let me describe how these kind of things will be used. So you can see that these 2 blue ones are public, and then these 2 red ones are private. Yeah. So in RSA, the public key means that the knowing of the E and N. And then how we encrypt the message is that, suppose there is a message, and then we will treat the message as an integer. I believe you now all know that how to transform a string to an integer. So you can transform string as an hexadecimal code kind of thing. Then that's actually the hexadecimal number for that string. Yeah. And then how we can apply the encryption is that, so we will apply E as an exponent to the message M, and then try to get the remainder when we divide that with the big number N. Yeah. And then RSA decryption is that, so we will apply the decryption as a exponent too. Yeah. And then how that works is that, so encryption is that the message exponent by the message apply the power operation with the exponent E, right? So ciphertext is like the M to the E. And then how we do the decryption is that for the ciphertext, we apply the power operation with D. So that's actually, C is a M to the E, right? And then that to the D. And then it will be internally MED, right? And then we made that E multiplied by D need to be 1 in this kind of the modular operation. So that's why we can decrypt the data. So it's somewhat complex mathematical operation, but the important thing is like we made ED to be 1, yeah, in this kind of the calculation. So that's how it works. So public key is E. So we will exponent message with that number. Then for the ciphertext, we will apply the exponent for another number that will become E multiplied by D will be 1. So that will revert the message into the plain text. And then this actually does not run the exponential operation on this. So there is a Euclidean algorithm that we can easily calculate the modulo of the power. So there is a POW function in Python, so that we can easily calculate that. And then let me show you how the things are actually working. So for this example, I created the RSA 4096 key, and then 4096 here means that this number N, the maximum size of this number N is in the 4096 bits. So it should be less than 2 to the 4096, so that number. But within that space, we can choose any kind of number. Yeah. And then this number N is defined by like the P multiplied by Q. So the P and Q would be the little smaller number than N, maybe the half in size, but by multiplying by these P and Q, we can get this big number N. Yeah. And then E is always 65537. I'm not sure you can read it or not. So the public exponent E is a 65537. And then we need to make E multiplied by D need to be 1 in the modulus of the P minus 1 multiplied Q minus 1. Yeah. So this is the D that we found. So this part D is not linked to the public. And then P and Q also not linked to the public. So the public part is just the N and the E. And then the interpretation is that if you know P and Q, it's very easy to calculate D. Yeah. So that's the thing. And then how the encryption works is that, so suppose the message is 1, 2, 3, 4, 5. Then, so we need to apply the power operation to message and then use the E. The E as an exponent. Exponent was like the 65537. And then N, we will like provide N as a like a modulo part. Then it will calculate the ciphertext like this. So because our N is like quite a big number, and then even if the message size is small, we are exponenting 65,535 times. So it will become a big number too. But as a result of like applying the modulo operation, so the older numbers, resulting numbers will be smaller than N, smaller than 4096 bits, and then that will be this message. But don't get surprised by this kind of weird number. So if we apply the power to this message, this number to the decryption key D, then it will result in 1, 2, 3, 4, 5, the original message M. So this is how RSA works. So any questions for like the RSA's internal operation? So that you can think it as like encryption is like the applying public exponent to the message. And then decryption is applying the decryption exponent to the message. And then E, D, if they multiply by together, then that'll be 1. So that's why we can get the message. So the good thing about like having this kind of the cryptographic setup is like that we can have encryption and decryption key separately. So to do the encryption, we need a public key, E and N. And then to do decryption, we actually need the private key D and N, but from the name of the public key, we already know the N part in the public key. Yeah. So like we only need to keep the D as the secret. Yeah. And then another property that the public key cryptography scheme should have is like the attacker cannot guess the private key from the public key. So in RSA, so even if they announce E and N to public, it's very hard to calculate D, because to calculate D, one need to know how N is factored by the P and Q. So because they need to get the P minus 1 multiplied by the Q minus 1. So the then number is required to get D efficiently. So in creating the key, what we are doing is like we are making the P and Q both are big number. So for example, if we are creating the 4096 bit of the RSA key, then the requirement for the P and Q is that like it is at least bigger than 2 to the 2047. Yeah, because the two numbers in range of the 2002 to the 2047 to the 2048, if two numbers are multiplied, then like we can get the 2 to the 4096. Yeah, so that's why like we are like choosing the biggest number enough for the prime numbers, and then that will make the factoring of the multiplication of that two number will be the super difficult. Yeah. So to describe it, this part in other words, so because factoring two numbers are difficult. So if two numbers are big prime numbers, and then we choose the key in that way. Yeah. So even if the attackers know N, yeah, they cannot factor this number, so they cannot calculate D from like the public key. That's the logic. then how can you use this kind of the public key? And then you guys have already created the public key for logging to our server, VMCTF, right? Yeah. And then how that works is that, so it will create the public part and then private part of your key. And then private part will be stored in your machine or your server directory. And then my server will only store this public part. Yeah. And then that's how it works. And then, so the good thing about this approach is that you can publicize the key. The public key is not secured at all. So that you can publish this. So like for example, GitHub. So if I go to github.com and then for any kind of user at the end, if I type .keys, then I can see that what kind of public keys for SSH they are using. Yeah. And then because these are not secret information at all, so it's okay to post it. So if I want Linus Torvalds want to be in the VMCTF1 server, what I can do is to just grab this public key and then create an account for him. Yeah. And then he can connect to my server. Yeah. So that we can use it in that way. So we can publish who I am, like I'm with what kind of key. So later you want to encrypt a message to me. So you don't have to search for the key. Just go to like get my public key and then encrypt it. And then, so what that means is that anyone can encrypt message if they know the public key. And then only the one who knows the private key, corresponding private key, can decrypt the message. So that is the beautiful stuff about the public and private key. And then to illustrate illustrate the difference between the symmetric key and then public key, symmetric key configuration, I want to elaborate a key exchange problem. So suppose we have 5 people need to communicate each other. And then suppose we are using block cipher. So in block cipher, we need to have a same key between 2 persons to encrypt the message correctly. Yeah. Then how many keys do we need to make each of them can communicate securely and privately? So the securely here means that no one else should see our message. And then privately means that like if A and B talks to each other, then C, D, E, or other entity should not know the message content. And then in block cipher, we need 1 key between 2 persons communicating securely. So if we want 5 people communicate securely and privately, then we actually need 20 keys, the 10 keys. So that's actually the same number of like the lines that we can draw between like the 5 people. Yeah, because like we need to have 1 key between like the each 2 pairs. Then, so in the block cipher, the encryption key is the same as the decryption key. So for n number of people, how many keys that we need is like the same as like the how many lines we can draw for the vertices of like the 5 vertices, 6 vertices, something like that. So that number will be the n multiplied by n minus 1 divided by 2. So it's in O(n) square. Yeah. So for the symmetric key configuration, to make all the participants communicate securely and privately, we need the O(n) square number of the keys. But in the asymmetric key cryptography, so we can have 2 keys, public key and then private key, and then encryption and decryption key will be different. Then what makes it easy is that we don't have to link encryption key to the sender. So any kind of sender can use my public key, the 1 key. So in previous example, if A want to encrypt to C, then A need to use AC key. If B want to encrypt to C, then they need to use a B to C key. Yeah, and then communication between C and D, C and E, they need to use different key. So even if like a receiver was the same, then we need to use a different key for by the sender. But in public key cryptography, we don't have to do that. It's because we can publish the encryption key. Anyone can encrypt with the single key. And then the only one you need to decrypt is the entity itself. So we only need ON keys. So for symmetric encryption, we need to have one key per each pair of the person. But in asymmetric key configuration, we can create a public and private key. And then each entity will hold their private part. And then we can publish all the public keys. Then anyone can encrypt to anyone securely. So suppose we have this kind of configuration. Then can A send encrypted message to B? That's a yes, because A can grab public key of B and then encrypt it. Then only B, the holder of the private key B, can decrypt the message. And then can C send an encrypted message to E? That's also yes. The C can grab the public key of E and then encrypt the message and send it. And then the E, they can decrypt the message because they hold the private key. So any pair can communicate to each other by publishing the public key. So in this case, we also need to have 10 keys. So the number 5 is not a good example. So ON square, we need 10 keys, ON, 10 keys. But take an example of like suppose we have N as 200. Then for the symmetric key configuration, we might need like around like 20,000 keys to make each people communicate securely and privately. But in the public and private key as configuration, we only need 400 keys. So including like a public and private. Yeah. So if we regard like a public and private key as a 1, then we only need 200 keys. Yeah. To let them communicate each other securely. Any questions about this part? So the implication is that the good thing about the public key crypto is like we can publish the public key, so that is not bound to any kind of sender anymore. So releasing of the having no sender on the encryption key, that release the complexity from like an N squared to N. And then this kind of the public key crypto, because of like it's a key asymmetry, we can use the scheme as a digital signature scheme. And then let's take a look at this in a different way. So in RSA, the encryption was applying public exponent to the message. And then decryption was applying private exponent to the message. So actually the operation itself is the same. It's just a power operation, exponent, applying the exponent. Yeah. Then what will be the meaning of the encrypting the data with the private key? So previous example was anyone can encrypt the data with the public key. Then I can only decrypt that. I'm the only one who can decrypt that because I hold the private key. But think about the opposite direction. So what is the meaning of the encrypting a message with my private key? So suppose I would like to say, I would like to donate $100 to OSU if I get A from CS370. Yeah. And then suppose I'm encrypting this message with my private key. So what that means is that, so message M, so I just translated this as an integer number, then it'll be something like this. And then our ciphertext will be, I will apply the private key D as an exponent. Yeah. And then I generated this message. Then any of you can obtain my public key because that will be public. Yeah. And then after you obtain the public key, then you can decrypt it. So that means ciphertext exponent E, that will be M, DE, M1. So like it will result in the same message. So that you will see that this kind of the message was decrypting by my public key. So that means we can actually verify that someone has endorsed on like some kind of sentence. The reason is that, so this ciphertext with the public key, we can decrypt it with this sentence. That means that the holder of the private key actually encrypted this message. Yeah. And then that can only be possible by the holder of the private key. And then we as a regular user, anybody can verify that that kind of sentence has been encrypted with the private key by running decryption using the public key. So it's something like, so if you want to sign some of the document, then what you can do is like get a SHA-256 of the document, and then encrypt that SHA-256 message with your private key. Then later, if someone wants to verify that document is correctly signed or not, then we will have that message, the hash message, and then we will have the document. And then we will decrypt this with the public key. So anyone can do, because like that requires just a public key. Then if that message is the same as the hash of the document, then we can say that the holder of the private key endorsed this document. So that's how we use the RSA in the digital signature as a digital signature mechanism. So the encryption using private key is so-called the signing operation. Yeah. The reason is that like the ciphertext can be decrypted by public key, so anyone can verify the result, but only the holder of the private key can generate that message. Yeah. So the implication is that, so if you are generating the signed message using private encryption, so that means you are actually leaving the evidence that you are the holder of the private key. Yeah. And then from the message of the semantic of the message, and then you are actually endorsing something with your private key. So let's do a little summary about the RSA. So the RSA is the popular algorithm that is in like an asymmetric key configuration. So it has a public and private key part. And then public key means that we can publish that in public, so it's not secret at all. Yeah, it does not have to be secret to make it the cryptographic operation secure. But for the private part, the private key need to be secure. Yeah. So that's the different thing. And then RSA is based on the difficulty of the having a prime factorization of the big prime numbers, and then like this kind of the factorization problem preserves the security by like not letting attackers correlate the private key from the public key. Yeah, if the two prime numbers are leaked, then attackers can easily calculate the private key. So like that should not be leaked at all. Yeah, and then in public key cryptographic settings, anyone can encrypt the message to one entity because the key is private, and then anyone can use to send the message. So there's no sender binding for the key at all. But the private key is only available to the key owner. And then because of that property, we can use RSA as a digital signature. So the encryption with using the private key means that only the private key holder can generate that kind of message. And then everybody else can verify that with the public key. So that's used as a digital signature mechanism. And then to compare and contrast the symmetric and asymmetric key configuration. So we could have a n square number of the key to make the participants communicate securely in like the symmetric cryptographic settings. So, and then another question could be, can we use symmetric key configuration as a digital signature mechanism? So we cannot do that because, so suppose we have only one key to encrypt and decrypt the D and E. Then if we use that key to suppose like the D want to announce something to E, then D will use this key to encrypt the data, but the E hold the same key, right? So if there is an existence of the message, then we don't know who generated that message, because either D or E, both of them can generate the message. There is an ambiguity. And then even if like a message was encrypted with the DE key, then only D or E can verify that. So public, they cannot verify the result. And then to verify if the sum of the message was encrypted with the key or not, yeah. So we need to leak the key. Then if we leak the DE key for the verification, then we need to generate another key for that. So there's a lot of inconveniences for that. But when we use a public key scheme for digital signature, then public key, digital signature using a public key is like we have the message with encrypted with the private key of the member D. Then we can decrypt the data using public key of the D. So then we know that the private key holder generate that message. So there's no ambiguity in like who generated the message. And also anyone can verify that because we can get the public key and then verify it. And then verification only leaks the public key. So there's no leak for the private key at all. So that's why like we can use a public key scheme for the digital signature, but then not for the asymmetric key, symmetric key for the digital signatures. Any questions? I believe the most important part for the RSA part is like not about the exponent, but about like you understand that like, we can use that as a digital signature. So the things are so for the encryption, anyone can encrypt, only me can decrypt. And then for the digital signature, only I can generate the message, and then anyone can verify. So that's how the two things are like working. All right, and then if there's no question, then like I will move on to the demonstrating the tutorial for today. And then the tutorial and challenge for today is a very small one. Yeah, so So I created a new challenge last night. So try to do fetch crypto again. Then you can see that the new challenge called the SHA-256. And then in here, if you run the launcher, and then what it says, please provide a file that stores content of the encrypted user, and then at the end, attach the HMAG of the encrypted user. And then how we will create the HMAG is like we will use SHA-256, and then apply the SHA-256 to the key first, and then attach with the encrypted data. And then run SHA-256 to get the HMAG. And then we will use the key as a CS370. So your task is to generate the HMAG of the encrypted user file. So how you can do that is you can start with the template.py. And then in here, so I put some of the code that like it will first demonstrate like how the encrypted user file was constructed in a hexadecimal digits. So the tool XXD will print out also all the hexadecimal numbers of the content of the file. And then after that, I will read the encrypted user file as an encrypted data. And then after that, we need to create a HMAC. And then what we will gonna do is we need to apply the hash to the key first. So hash function is SHA-256, and then key is CS3070. So how we can generate the first hash message is that we can create the SHA-256 object, and then input the key, update, and digest. So after creating the object, you can update with the data, then h.digest, that will generate the hash value for you. So this is the example of how you can get the key part. And then what we will gonna do is we will construct the message as hash of the key, and then we will attach encrypted data on top of it. Then it will go to the message as a hash, a message to the hash, then it will generate the digest. So it will get the HMAC, and then how it will generate the file, hmac.user, is that it will have the encrypted data first, then attach HMAC at the end. And then I just added the message as like using the hash of the key and also the encrypted data as an input for the HMAC. So this part, so adding the hash of the key and then encrypted data was in here, and then this will generate the correct file that is attached with the HMAC. So take a look at these messages. So these 8 lines are from the original encrypted.user file, and then we calculate the hash of the key, the SHA-256 of the CS3070 as this one, and then that value goes into this part, and then adding the encrypted data, and then hash it, and then we got like the hash HMAC as in this one, yeah, 36E8CF something, and then that kind of the 36E8CF, that kind of the 32-bit bytes, 256 bits are added at the end of the file. So this is how you can attach HMAC. And then, so now we are seeing that 36E8CF something, that kind of value for the correct one, but suppose I change the message a little bit. So I'm simulating some of the attack. Then suppose our encrypted data is something like so I split the encrypted data for the first 10 characters and then the rest of that, and then remove 1 character and then change that character as an A. So what I have done is like I'm replacing the 11th character into A, that forcefully overriding that. Yeah. So that I just change 1 byte. And then I'll run it. Then you will see that the HMAC is totally different. So it's not about the 36E8 or something. So it will have the totally different value. And then that's why if there is any kind of edit of the data, then we can detect that. So actually this one got edited. 09 was edited as a 61. But even for the very small change in a byte, then it will result in like different values. And then let me change it to the somewhat similar value. So it was 09, then I will change it as a 08. So 09, 08, I just changed 1 bit, but that also changed the value a lot. It's not even close to 36E8 or something, yeah. And then, so if you have a wrong HMAC, no, this should not be correct like this, yeah. Yeah, this is my bad. Yeah, I made a mistake on building the challenge. So it should compare the HMAC with the encrypted user, but it just uses like the your it just uses like your input. So that's why it works for the like the edited message. So you should not work on that. Yeah. So the important thing is that like if you change the encrypted data a little bit, then it will be shown as a change in the hash drastically. And then because like you cannot guess what will be the message that generates this string. Yeah, you will never guess that because cryptographically it is designed that like making that hard. Yeah. So after attaching the HMAC correctly, so if you run the program, then type the file, then like you can get the flag for it. Yeah. So this is just for like the practicing and knowing how you can generate the SHA-257, 256 with the programmatic manner, and also like how you can play with those things in a Python. Because starting from next week, when we get to the network security, we will use a lot of like the hash and Cipher in Python to communicate with the server. And then you actually need to decrypt and matching some of the HMAC to get the flag from now on. Yeah. So they just take this challenge as like regard this challenge as just practicing. You are generating the hash and then MAC for that. So the only thing you need to do is like filling this line for this challenge. All right. Any questions? All right, let's finish today's lecture at here. And then please feel free to work on the challenges. And if you stay here, then I will try to answer your questions.